They use the ratio.
Yeah, it was.
It's okay. It's a ratio. Because n minus one.
Yeah, it's not small.
It's not like ultra.
Yeah.
Get rid of the 3 to the end and
You can.
You have to do a bunch of that, like, that ratio test.
I'm gonna
crash,
go
because, like, it just
Okay,
goes
so-
to infinity.
I have like 40, 58 dollars over here.
No.
But
No, so you try to do a ratio
you have to
test.
check the limit to prove that it's an alternating series.
Yeah, but I think the limit
Yeah.
itself goes to
I think I'm gonna go to,
Yeah, how do you?
where it goes to 3 over 2.
I've changed a few things around.
Because like if you,
Well, that's just
Right.
three to the end.
But that works the same thing.
Yeah, either way, it's greater than one, so.
but like, yeah, because it's, I don't know if you can get rid of it, it's just ln of 3 or ln of 2.
But if that was convergent, then
Chris,
that's
are you
when you
ready?
have to do the ratio test to figure out if it's absolutely convergent.
You okay?
Yeah, just don't know what to do with it.
Can you do, one over n would be nice.
That would be convergent.
No,
Oh, wait, no.
that's another reason
One
why
over
it's
n.
divergent, is because it's divergent times divergent. Because
Yeah.
it's two it's a ratio.
Where is this?
The first one,
Yeah.
Oh.
the first one's, it's E series times a ratio.
Well,
Or a geometric series. And, both of those independent pieces are divergent, so multiplied together.
That's
Yeah,
amazing.
because the limit is the
Are you
same.
allowed to do that?
I don't know, but
I
like,
know you can add limit, I don't know about the alternate series, or the ratio.
You like.
but if something that's not zero,
Let's see, limit of
That's this.
this is last night's homework. Then this is the night before it's homework. And then that's a different one.
They go.
And then it's somebody authorities. Yeah. 3 nights of math
That looks
homework
like
and
a
2 days of notes is not fun to do every night.
Wait,
Is it 1 over n squared?
Second one.
I need integration. I had a question. Integration.
Yeah.
There's gotta be a better. way to do
26.
that.
It like.
Integration.
So you could change 1 over n like that. Like,
Really,
can
I
we-
don't wanna do that?
You 1 over n.
Why don't you
No, you
just,
can't do that.
why don't you just limit compared to, 1 over n squared?
And I was just a little.
I feel like that-
Oh, yeah, because I don't
No, that would work.
really like.
You
know, you
No.
you can direct
You could
comparison.
also direct comparison would be easier.
Direct
Yeah.
comparison
No,
to
because
ratio.
No.
Well, it's just
Natural
a-
log of n over n squared is gonna be a target.
Well, it's gonna be-
So
Direct comparison.
this is gonna be.
No, because 1 over n squared is
It's
convergent,
smaller.
and then that's gonna be bigger than ln of n over n squared.
Well,
that's
that's
what
what
I just
n
added.
squared
Plus
is
one,
larger.
so
Yeah.
Not
Yeah.
at one.
It's
Yeah, which would converge
Oh, that's
because
right,
1
yeah.
over n squared is convergent.
Because I think it was written.
Yeah, but you can't tell anything from that.
Yeah, that's correct.
It's a,
I'm
that
not-
one is above it.
Yes.
So,
I guess you're right.
Okay. Starting around. You can do it, guys. Thank you.
Yay.
So you have to integrate it?
There's like
I know.
Or even do that
I know,
ratio
it's
one
weird.
that they were talking about.
Amazing.
Usually we're
Ratio.
flipping through.
Amazing, I know.
Okay.
Like, that's that weird one, like, if it comes out with a positive finite interval.
And then, wait, okay, and then you can just cross out
The
the
first
n
one's
squared and
yeah.
then it's ln of n. That's it.
Divergent, yeah. Yeah, but,
One over n.
yeah, but
This
one over n
seems
is
too
also
easy.
divergent.
So like, but are you let's split up?
Well, we're testing if it goes to 0.
Yeah, but something that doesn't go to 0 times something that doesn't go to 0 isn't 0.
But 1 over n does.
If it's just over n.
Well, yeah,
Just
but
say.
If it's divergent.
because of P series. We're still on one.
Okay. I should say. I'm gonna skip in 2 as well.
It
2
was
isn't bad if
skipping the
I
entire
limit
one.
comparison to 1 over n squared isn't bad.
How do you do that?
Well, then, yeah, so it's just.
So you just like do the
Well,
ratio.
number 3 worked out.
You
ln
just
of
do
n,
1 over the other.
And
So
then,
you just divide it, so you multiply it.
yeah, but
so-
then how do you, what's the rules again, like if it's a positive positive finite, and it's
Positive finite, then it's just the same thing. If it's
as someone.
not positive finite, it's the opposite.
Okay, so if you
So-
compare it to something that's divergent, you get positive and finite, then it's divergent, but if it's not positive finite, it's not.
Oh, yeah. You really don't have all of the tests. I need to.
Writing numbers and
Did you use the ratio test for? Does the n plus 1 go to 2n plus 2 or just n plus 2?
N plus 2, I think.
Yeah, that was.
Can you get like 2 over times?
I mean,
Yeah.
And the sum between n squared.
Yeah, they just
Indeed,
cancel
as
out.
Oh, no. Not at all. That's just too much.
I'm so scared for that.
I don't get it, it's not just our class that has an absolute treat of the week.
No, I have a bio test.
No, so many people are being great,
I know.
which means that.
On Thursday, we got the math quiz first, so I jumped right over to the honors chem test, and I jumped straight over to
We did.
like this essay thing for language arts, and then I go to econ midterm. Yeah,
It's a fun day for you.
I am really looking forward to Thursday.
Last test.
yeah, but it's
Wait,
very,
what?
it's a big test.
Well, it's 2 more.
No, it's the last one.
Still,
last
wow, we're only.
No, the finals project.
In this class?
No.
Yes.
You wish.
Don't get so excited.
he's shaking his head.
You wish.
Oh my god. This definitely is wrong.
I think Mr. Pointer is realizing that we're getting up because he's.
Yeah,
Did you get that one to work out?
Yeah, he's also.
I think so, I gotta converge it.
He's just done. Did you get 2 as divergent?
Yes.
Cool, because I got like infinity.
Oh, he's shaking his head.
I don't think so.
I said it was convergent because, because I let me convert it to square.
But
Yeah,
that
but they
doesn't
did
work.
that one over in squared and then it just everything.
Oh,
comes
wait.
from zero, like it's
Well,
LA.
hang on here. 1 over n squared is less than that.
Wait, it's a lesson?
Well, 1 over n squared is less than the natural log of n over n squared.
Oh, wait,
And 1 over n squared converges, but it's below it. That doesn't help.
Oh, yeah. What was,
That doesn't help, right?
Oh, wait, does
If you're trying to show convergence, you have to have something above it that can, if you're using the direct comparison test. I'd use the integral test. I believe the integral test shows. I think, I'm just off the top of my head.
Do you have
I could be
to
wrong. I know it's close to convergence or divergence. Yeah. Sorry. It's
I
good.
tried to do like the ratio, or not whatever the other one.
I wouldn't use the ratio test, just because the natural log is weird.
The one that we learned with the direct comparison, that's like direct comparison.
Limit comparison?
Yeah.
What would you limit compare it to?
Over in squared.
I don't think that's gonna work. I think you're either gonna get 0 or infinity.
Yeah.
Remember, neither of those results work, right? It has to be positive and finite,
That's why I was confused, because I
Yeah.
got infinity and I was like.
which is why that you're gonna have to use the integral test.
Oh, so it only gives you a positive, like it only gives you an affirmative answer. It can't give you a negative
Right,
one.
exactly.
Oh,
It's, yeah, guys, listen,
that's really
the
nice.
limit comparison test, it's not like opposite day if the test fails. The test literally fails. You have to choose another test, right? So a limit comparison test is like 0 or infinity. It's like, you can't just be like, hey, sweet, I just flipped it. No, it's not the way that works. Now, hang on here. The alternating series test is like that, right? The alternating series test, it will converge if it meets conditions 1 and 2. If conditions 1 or 2 fail, it diverges. But it's not like we're back with the limit comparison test. I do. So Grayson, you got, for 2, you got conversion. Convergence.
Yeah.
Okay. Juliana,
I think
you
I
get the
got
second one?
converted.
But I'm
Did you get it
sure I
converged?
don't know how to do parts.
Cake.
Is number 2 convergent?
I think so.
Instead of-
Juliana and Grayson said yes, so it has to converge. Yes. Must converge.
That's the room's just ordered. It was on for a while.
Oh.
Yeah,
That's
it's
helpful.
a couple steps.
So what about say? Secular.
3's kind of a mess, guys. Sorry about that.
3.
You did good.
No,
I like the
three
ratio
I like
test.
when they cancel.
I do
the
too.
ratio
It's so
test.
pleasing, isn't it?
3 is really
If they
hard.
don't cancel the ratio.
It's like, do you guys remember in undersized for 2, those like horrible, like rational functions that you would multiply and add them, and like you would get to the end and like nothing would cancel. And you're like, are you kidding me? I just spent 10 minutes on this. Nothing cancels.
Well, nothing
That's
was child,
child
and then
abuse.
I'd always just go, huh, must have gone wrong.
Well,
Did we figure out what to do for number 1?
No.
I didn't. I did it. What did you use? I didn't. I don't know what is it?
guys, on 1, don't use the root test. That n is not being powered by an n. It's not clean, right? Because you're gonna get n to the nth root. It's horrible. Don't do that.
Yeah, this is like-
Ratio it.
Wait, but
Ratios, I think, are really good at mixed nth powers and non-powers and factorials. Ratio test is perfectly suited for that.
But the limit is infinite.
That's okay for the ratio test. Limit comparison test has to be finite and positive. That's the only one for which that's true. If you're using the ratio over the root test and you get infinity as a result, totally good. If you get 0 as a result, totally good.
Oh, but I was trying to do like an alternating series with that.
I think the alternating series test is tough on that as well, because you've got to, for step number 1, you have to make sure that that drives to 0. That's hard.
Yeah.
That's not an easy multiples rule. It's not super conclusive either, I would say. The ratio test takes care of all of that. Because, check this out, even though this is alternating, guys, ratio test and root test will tell you about absolute convergence. So you don't even need a second test. It's everything's all in one.
adding like things.
Yeah.
Number 3. Are you getting your new carpet installed during the
Yeah.
school year?
We're
When
gonna be
is
moving.
that?
We're gonna be
Are they
moving.
carpets everywhere?
I know.
You can't.
I'm more bummed than you are, trust me. I gotta move everything. So I don't know where we're going. I have to tell you, but it's gonna be in April. And I don't know if we're coming back.
So many great
You
images
just
for-
got the board.
I can't.
I just got the board.
Where are we moving to?
It's just-
I don't know.
Oh, I think you just.
And they're just gonna paint it like something kind of like that gray. But it's-
Is it
I
the gray?
literally,
Is it the gray that's in G-Hall? Because it looks so sterile.
What?
They're gonna paint behind the board.
I think just paint over it. I don't know what they're gonna do. I hope they realize that's a mimeo. That's kind of tough. It was hard getting the paint in around the pens, but we got it.
Yeah, super glue the pens on that way, the sock will going around and try to paint it.
We're almost done. Because it is Tuesday, right?
yeah.
We don't have to go.
I'm ready.
Think you're ready? But you're uncertain. Another minute or two? Probably you're still working, right?
No,
Giving up? Which one are you stuck on? Third?
I just messed something. Yeah, I messed something up on 3, I think, and I.
This, I think this is gonna kind of help us with 26 and 28 on the homework. I'm hopeful. If not, I can still work those, but this is pretty similar to those types of problems.
I like that before we even ask, you just know which ones we're not gonna.
Well, yeah, I've been doing it for a while. Are you still doing number?
Oh, no, I'm done.
Okay.
Kyle, you do okay?
Yeah, I'm just like not quite getting, like everything's just slightly off on number 3. I'm not sure what I'm doing.
Yeah,
Okay. Diverge.
I guess I'm
Yes.
done.
Using ratio.
You got converge?
That's a good ratio.
Yes, but because I got it's bottom heavy.
I ended up getting it since 3 to 10 times.
I think it was.
I
You got diverge?
I got diverge.
You got diverge. Okay.
I don't know.
I know this. It's one or the other. And we're gonna find out.
I probably.
Yes.
I just get one, yeah, it's not nice, but
I
that's
never
right,
got
then we're in plus 1.
Did you got
I don't know if you
Again,
looked at
times
it,
2.
but
So then
You can.
add that.
Yeah, but I don't know if you have.
Yeah, you still can.
Yeah.
So,
yeah.
So, yes.
any of those tests, Kat, where you're taking the limit,
Oh, yeah.
you have to look at it if you do. If it's in the truck.
Yes.
It's bottom.
I don't know if you got that.
Ready?
Right. I want to see your.
Oh, yeah.
Well, it's definitely one minute. You don't have to cancel everything else.
Well, bottom heavy is just gonna go to 0.
Oh, yeah.
Now, keep in mind though, guys, remember, bottom heavy within a test indicates one thing. bottom heavy of just the sequence indicates something else, right?
Yeah.
So bottom heavy of this just indicates that this has a potential for convergence. That's all that tells you, right?
Which is enough.
Which means more work to do. All right, should we dive in?
Yeah.
Okay, let's do it. So as I was telling you guys before, I think it's difficult to determine whether that a sub n thing goes to 0, right? Yes.
I was kind of wondering, so if you got like 1 over n times like 3/2 to the n, right? Both of those are divergent by themselves, and if you take something that's big times something that's big, isn't that just bigger?
Correct.
So can't you just know that that's divergent?
You mean you want to split them and test them separately?
Because if they're both big, then that means that they don't work.
That would be the only case that you could use.
Because that's
Yes,
when
convergence.
the nth term test kind of.
Mhm. Yeah, and that is possible because, wait, hang on here. No.
Oh, I got you.
Yeah, you got me thinking. The summation of a product is not equal to the product of the summations.
That's really not.
That's the problem. So let me think about that, all right? I don't want to give you an answer that's incorrect, so let me think about it and I'll get back to you. All right, so do you guys agree then that the ratio test, I think, is definitive, and it also takes care of absolute and conditional convergence, right? And you don't have to worry about taking the L'Hopital's, determining what the sequence goes to, right? So it eliminates you from having to prove step 1 of the alternating series test. So let's do it. Let's take the limit and we do the ratio test, yes? So this is going to be 3 to the n plus 1, n plus 1, 2 to the n plus 1, 2 to the n, 3 to the n. Absolute value.
Just leave off the alternating bit because it doesn't.
Leave off the alternating bit, you just the absolute value of the ratio of the two, right? You got to remember, it's a sub n plus 1 on the top, a sub n on the bottom, otherwise this is not going to work, right? So let's start canceling. I got one more 2 on the bottom than I do on the top. You guys just slow me down if I'm going too quickly. One more 3 on the top than I have on the bottom. Chase, you with me? I'm going to L'Hopital this. This goes to 1. The answer here is 3/2. That indicates what? Divergence by the ratio test. Good. How many guys?
I did
Okay.
think of 3/2, but it wasn't right.
Got it. Okay. It was like, yes, okay. It was the other 3/2. All right. Should we
Proof alternating series?
wait one more time?
Do you need proof alternating series?
It doesn't. In fact, absolutely. This, well, there is no condition of divergence.
Okay.
So it just diverges. Just diverges. And listen, you're using the ratio test, right? So there's no need to mention
Well, wouldn't
it.
that be absolute divergence?
The absolute divergence, but again, there's, yeah, it's a little bit redundant, but that's okay. All right, here we go. I'm going to integrate natural log of x over x squared dx. My u, Grayson, is what? ln x. My dv then is x to the negative 2 dx. It's important that it's location sensitive for parts, right? All right, Juliana, du is over x dx. V then, Tim, is what?
Isn't that- Oh, wait, no, the other way. Yeah, negative 1 over.
I think it's negative 1 over x, isn't it? X to the negative 1 over negative 1. Beautiful. Let's put it together. This is negative. I'm sure these guys can see. I've got negative ln of x over x minus a minus x to the negative 2 dx. Everybody good? Negative ln x over x. This is going to be minus 1 over x going from, what is this, 1 to huge. Let's plug in huge. ln x over x, that's indeterminate. You guys agree? This is 1 over x over 1. This goes to 0 minus 0. I'm not showing the L'Hopitalizing, but I'd like you to show me it on the test or quiz. Is everyone clear on what's going on here? Minus then what I get when I plug in 1, that's going to be 0 minus 1. This is convergent by the integral test. Yeah, Jason.
If you get a 0 there, does it do anything?
If you get a 0 where?
Like if you 0 minus 0 minus 0 minus 0.
It means convergent.
Oh, okay.
Yeah.
So it zeros don't matter here.
No, still considered finite, right? And it's determinate, right? Any other questions on this? We good? All right, let's tackle this sucker. Here we go. Remember, when you're using the ratio test, it's kind of like functional notation, right? A sub n plus 1 is like n plus 1 goes in for n, wherever you see an n, right? So isn't this going to be then, if I take the limit as n goes to hugeness, this is going to be 2 to the n plus 1. That's n plus 1 all over 3 to the n plus 1. 2n plus 2 factorial.
Plus 10.
Yeah, isn't
Exactly,
this
times 2.
2n plus 1 factorial? It's like functional notation. Wherever you see an n, n plus 1 goes in there. Over the original, right? So this is just going to be the flop of the original. This is 3 to the n, 2n. Look at all the cancellations, Jackie. This is 2 to the n, n plus 1. Absolute value, right? Which doesn't really make any difference here. Sweet. Let's get rid of stuff. I got one more 2 on the top, one more 3 on the bottom. It's got deja vu all over again.
The explanation.
Right on. Hang on. Let me just write it down here. 2 on the top, 3 on the bottom, right?
2n plus 2.
Yeah, let's do this. Do you guys agree that this part locatizes to 1? Everybody with me? These then, we got to figure out this. This is going to be 2n minus 1, 2n minus 2. This is going to be 2n plus 2, 2n plus 1, 2n minus 1. We're going to stay where I'm getting these. Sweet. So this cancels from here on down, there on down. Definitely bottom heavy. This is going to 0. Do you guys agree? Which indicates what? Convergence. In fact, this converges by the ratio test. Yep, Jake.
So kind of talk about what Tim was talking about earlier. So you couldn't bring out like a 2 to the n over 3 to the n right off the bat and then say that that's like a convergent geometric series and then just test it.
No. Listen, guys, if you're starting the ratio test, you can't switch halfway through to the geometric series test. No,
If we switch it before we even start any of the
No.
tests.
don't. Stop it. You just pick a test and go with it. Like, for instance, I couldn't do if I'm doing the ratio test and I get over here and I'm like, hey, it's 2/3. Hey, that diverges by the nth term test. That's not what this is telling you. This is the outcome of the ratio test, right? Chase.
How did you locatize before it was in there? Let's do it for example.
Well, I am taking the limit of each one of these individually, essentially, right? The limit of a product as opposed to the integral is equal to the product of the limits. So I can do them separately. So n plus 2 over n plus 1 grow at exactly the same rate. I locatize those to 1 over 1.
I mean, or you could just keep those in there, so it's still on heavy.
Yeah. Yeah, you could keep it in there. It's going to be cubed.
It's still gonna be
It'll be something cubed on the bottom, right? Because I got to get straight to the notes, please. Okay, sorry. This is too long. The questions you guys are asking, though, are really, really good. So keep it up. But 8-7, this will not be on the quiz, okay? If you have more questions that I didn't get to, I can do it tomorrow morning during advice, okay? So 8.7, here's what we're doing today. We talked about this briefly yesterday. We're going to be using infinite series to help us estimate functional values. Now, this technique is actually super useful in electrical engineering. So this technique does. So if any of you are thinking of pursuing that or end up pursuing some of those classes, this technique is actually pretty valuable. And it seems like you could just be able to do it with like software, but this is actually an estimation technique that we use later on. So there is, I guess, some value. It's not just like theoretical in nature. So here's what we're going to do. We're going to take things that are difficult to approximate, like functional values for e to the x, for instance, right? Without a calculator, that is super, super difficult. I'm going to show you a way to do that with polynomials. Okay, that's the goal of today. So this is 8.7. And this is, what do they call this? These are polynomial approximations. Okay, so I'm going to spare you like the algebra. I don't have time to work through the algebra with you, but essentially here's what we're doing. If I take e to the x, something like this, and I want to build an approximation for this function right here, at x equals 0. And by the way, you can build these approximations at any x value that's in the domain of the original function. I'm going to first off assume I'm going to look for a polynomial that has the same functional value right at 0. So it shares the same point and it shares the same slope. You guys all with me?
Yeah.
Okay, good. So at x equals 0. So check this out. You would say that p sub 1 of x, this is a first degree polynomial. That's the notation for it. This turns out to be x plus 1. Right? And again, I just don't have time to work through the algebra on this. So what you get is something that looks like this, right? There's your x plus 1. Now, I could use this function to estimate what e to the x is around values really close to 0. It's like super useful, right? Like if I want to know what e to the 0 is, I just plug 0 in here and I get 1, right? Also, if I was looking for e to the 0.001, I could just plug it in here and get something actually really, really close to it. But you guys can tell, the farther you get from 0, the worse this polynomial approximation is. And so what we do is we step up the power of the polynomial approximation. Suddenly we say, I want not only the slope and the functional values to be the same, but I also now want the concavity to be the same there as well. And what you end up getting when you work through the algebra on this is you get p sub 2 of x, and you get 1/2 x squared plus x plus 1. And again, working through the algebra is not the important part here. Here's the important part. When you have a second degree polynomial that looks like this, you can take my word for it, but when you graph it, you get something that looks like that, which is a little more accurate, a more accurate approximation of e to the x a little farther out, because this more closely approximates e to the x in the straight line. And then we just keep bumping it up 1 degree at a time. The idea is to eventually get an infinitely powerful polynomial that looks like e to the x. In fact, the higher the power, the more closely resembling e to the x the polynomial will be. So like your third degree might look something like this, right? Might come in, yeah, it's going to come in and do something like this, right? And it'll be really good at approximating e to the x, even farther out than the square, than the quadratic. But at some point it starts to fail again. And so we just bump up the approximation. So I'm going to show you how to build those really quickly and efficiently right now. Basically, it's a formula. There's 2 formulas you got to memorize, all right? They're pretty easy to memorize. You get through a few of these, it really starts sticking in your brain, okay? And these are called Taylor and MacLauren polynomials. So let's put these on the board right now. Okay. So here's the formula. We're going to put this in our memorized box. MacLauren polynomial, p sub n of x. Is going to be f of 0 over 0 factorial times x to the 0 plus f prime of 0 over 1 factorial x to the first. Sorry if you guys can read this. The board's still just a little bit wet. Plus f double prime of 0 over 2 factorial x squared. And you just keep up this pattern until you get the nth derivative of f evaluated at 0 all over n factorial x to the n. Change this. This is actually a Taylor. The MacLauren polynomial is a more general polynomial estimation, p sub n of x. And by the way, this Taylor polynomial right here is centered at 0. right? This is like the e to the x picture that I showed you before. This is c is equal to 0. And this will be c other than 0. You can really just use the second one. It fits no matter what, which one you have, right? So I got p sub n of x is equal to, this turns out to be f of c all over 0 factorial x minus c to 0 plus the first derivative of f evaluated at c over 1 factorial x minus c to the first, and so forth. All the way out until the nth derivative of f evaluated at c all over n factorial x minus c to n. All right, so let's go ahead and build one. You guys got that in your notes? All right. So maybe I'll just leave that up there. I think I got enough room over here. So how about this? Let's build. Let's build a fourth degree polynomial for f of x is equal to 1 over x centered at 1. All right, so I think that the only part that's a little tricky that really requires work here are these numerators, right? You need the original first, second, third, fourth degree derivative evaluated where you're centering it at. That's really the only like side work you have to do. Other than that, you're just actually plugging this directly in using those numbers. Bless you, Connor. So let's go ahead and figure out the numerators over here. I got it up here. I've got f of x is equal to 1 over x. F prime of x then is equal to, when you derive that, what you get? What's the derivative of 1 over x? Yep, good. Negative 1 over x squared. So f prime of 1 is equal to negative 1. F double prime of x. What is that? I think it's 2 over x cubed. Yeah, positive 2 over x cubed. You guys agree? Positive 2 over x cubed. So f double prime of 1 is equal to 2. F triple prime of x is going to be negative 6 over x to the fourth. I don't know. Is that true? Thinking. Oh, man. Tuesdays kill me. So this turns out to be f triple derived evaluated at 1 is equal to negative 6. And then lastly, fourth derivative of x is going to be equal to, what is that, 24 over x to the fifth. So f derived 4 times evaluated at 1 is 24. Does everyone understand what I'm doing? Okay, can you see it okay? All right, perfect. So I'm going to build this polynomial. I've got p sub 4 of x. Turns out to be, oh, by the way, I should say f of 1 is equal to 1, right? It's just 1 over 1. All you got to do is build it into this formula, and you got it. P sub 4. 1 over 0 factorial x minus 1 to the 0 power. Going to be minus 1 over 1 factorial x minus 1 to the first. That's going to be plus 2 over 2 factorial x minus 1 to the second. And that's minus 6 over 3 factorial x minus 1 to the third. Plus 24 over 4 factorial x minus 1 to the fourth. I don't need you to FOIL this stuff out, but I would like you to clean it up just a little bit. Okay, so this, my P sub 4 of X turns out to be, this is 1. By the way, we talked about this yesterday, right? 0 factorial turns out to be 1. It's defined as 1. So this is just 1 times this to the 0. That's just 1. This is going to be minus 1 times X minus 1 to the first. It's going to be 2 over 2. That's 1 times X minus 1 squared. That's 6 over 6. That's minus 1 X minus 1 cubed. 24 over 24, that's plus X minus 1 to the fourth. And you can leave it just like that. How we doing? You good? Sound good? All right, then later on, they're going to say, hey, listen, why don't you use this polynomial, 4th degree polynomial, to estimate f of 1/2. And why wouldn't you do this? Guys, listen. If this is your function, you're trying to evaluate it at 1/2, why would you use this? I mean, come on. It's super difficult. I'd rather derive it and put it into this gigantic formula and use this to figure out what f of 1/2 is. It's so much more practical. Okay, now listen, I know I'm using a ridiculous example, right? But if it were like e to the x, right, then this would be obviously more useful. It is ridiculous to use this for f of 1/2. It's 2.
Okay, good, I'm not going insane.
You guys with me here? But I'm going to have you do some where it's not so obvious. Yeah, that's how you plug it in. How we doing, people? By the way, if I did get this, right, if I did P sub 4 of 1/2, you guys agree I'll get 1. This is going to be minus negative 1/2 plus, what is that? Negative 1/2 squared minus negative 1/2 cubed. It's going to be plus 1/2 negative 1/2 fourth. You guys all with me here? And isn't this the same roughly as the sum from n equals 1 to infinity of 1 times 1/2 to the n minus 1? You don't need to do this. You don't need to come up with this, but I'm just saying, I think that, is it not?
Like have to calculate e to the exponent, you end up getting like e to the like -1 or something. That'd be like difficult thing to calculate.
Yeah, it would, which is why if I have you build even the x, I'll probably have you set it. So the assumption is you know that it's equals 1, right? But yeah, e to the third or something like that, it's going to be equally difficult. Your estimate is even as hard as figuring out what the actual function is. Yes. So this is of limited usefulness for sure. All right, questions? This is literally all you're going to be doing. You're just going to be going through the mechanics of building these polynomials and somewhat simplifying them. That's it. And then also using them to come up with a polynomial estimation of it. Now the idea is, guys, that this is going to be somewhat of a shaky estimate of my functional notation, of my functional value, right? The idea is to build a more powerful polynomial estimation. The more powerful the polynomial estimation is, the closer the approximation to the functional value. Tim?
Yeah, I was kind of wondering, you said this is still like useful in electrical engineering, but it's still an approximation, and wouldn't computers be able to find the
It is. But the nice thing is, and you're going to see this eventually, we're going to be building, they call these things power series, by the way. You don't need to worry about that. But these infinite series that we're going to be building actually do converge to the actual functional value. They actually will give you the functional value.
So this is what a computer does in fact.
Oh, yeah, that's exactly right. And then we're going to be talking about functions that can be not estimated, but determined exactly just over like a given interval. And outside of that interval that it fails, basically. We're going to study all that stuff. All right, here's what I'd like you guys to do for tomorrow, please. Actually, let's make it do Friday, since we're going to quiz. You guys can work on it after the quiz then tomorrow. Quiz is 8-1 through 8-6. Okay. Where you don't have to worry about this stuff tonight. Page 615. 13, 17, 20, 25, 27, 29, 41, 43. So I'm not giving you a ton of these. And actually, guys, I'm embarrassed to tell you this, but I actually have these backwards. I had it right the first time. It doesn't really matter what you call it, but they're polynomial estimations. Taylor is the 1 center negative. MacLauren centered at 0. Sorry. Should we play guess the cent?
Yes.
Even though Jackie always wins, and she's already won.
I already got that.
And it's not detangler.
I guess the rest should be.
She did. She was just like, easy. Go, Jake.
Apples.
That's right. You were already here, weren't you?
I was.
Yeah, see? See?
Green apple.
I was gonna bet apples.
It is orchard apples.
Regular apples.
No, please.
Oh, no.
Come on, use your scent. I mean, use your nose.
Come on.
Colin, that's ridiculous. Apples.
Yeah, that is like, that is way too.